one thing we did last time is we said, well, here's the original policy gradient theorem, and we derived a particular algorithm from this called reinforce. And we said that it had high variance. That's one of its major issues. It has unbiased gradient estimates, but it has a high variance. And we said one reason for that was the Q function itself sort of factors in both how good is the state and how good is the action in that state. And so you could be in a really good state and take a bad action for that state, and that might look better than if you're in a really bad state and take the best action in that state. And the Q function has the state value information embedded in it, which can make learning a little difficult because the learning algorithm has to sort of figure out what part is due to the state and what part's due to the action. So what is often done and almost always done in policy gradient algorithms is they introduce a baseline. And we introduced the baseline variant of the policy gradient theorem, which basically says you can subtract off any function of a state. So any function that's just a function of the state from this Q function, and things work out. You get the same equality here to the gradient. We went through the proof of that, which was relatively straightforward. So that's the first thing we did last time, and then we said that a very common baseline, and it's pretty. Yeah, I can't say that any algorithm that you see these days will use a baseline other than this. Maybe there are rare exceptions, but the most common baseline is to use a value function estimate of the policy that you're trying to learn. So you'll have some value function estimation routine going on as you're learning your policy, and that will be your baseline. And this sort of agrees with the sort of the intuition setup that I gave you, that we kind of want to factor out the part of the value in the Q function that's due to just the state itself, and rather we'd like the policy gradient to focus on really what's the influence of the action itself. And so, this term here, Q minus B, you can think of it as, how much better, is A than sort of the average behavior I expect to see by just running the policy itself. So that was the idea of the baseline. And this is a term that you see a lot in reinforcement learning. The advantage function is just the Q function minus the baseline. Maximizing the advantage function is the same as just maximizing the Q function if you're in a particular state. But this advantage function will have most of the variation due to the action as opposed to also variation due to the state. Right? So even though maximizing, they're sort of the same thing, numerically, when you're doing estimation, it can help a lot to use the advantage function. All right, and that's so widely used. Some papers will use the advantage function without even defining it. It's just a very, very commonly used definition. All right, so we have our new version of the policy gradient theorem, and then we said, well, a very simple addition to reinforce would be, well, we'll still use this Monte Carlo estimate for the Q function, right? So we're going to use Monte Carlo, the sum of the rewards after we take an action in a state, to be the estimate of the Q function. But as we get experience, we're going to be always trying to update an estimate of the value function of the current policy. And we can use whatever technique you want. You could use Monte Carlo estimation techniques. You could use TD techniques. We'll look at that today as well. So we had a whole slide deck on estimating the value of policies, right, using reinforcement learning. And this is where it becomes relevant in practice. So we gave code for that. Pretty straightforward. So this is your estimate. Here's our advantage function. And this is an estimate that's always evolving. And then we have two sets of parameters. The weights here, W, are for the value function, and theta here is for the policy. You can see very similar estimates, right? Very similar update equations. We'll have different learning rates for them. The only thing that differs is sort of the form of the update here. And generally, if this is a regression problem. Learning the value function is a regression problem. You're trying to predict a number, a value. And generally for regression problems, you're just going to be dealing with the gradient of the actual function you're trying to estimate. It's kind of strange perhaps to see the log there. This falls out of the policy gradient theorem. I'd love to go through a proof in the class, but I don't want to take the time for it. But usually what you'll see is if you're doing gradient descent on a policy that is a probability function, right, or anything that's a probability function, right? Remember, this policy is a probabilistic policy that is defined to have a probability for each action in a state and sum to 1. Generally, when you're doing gradients on these things, you'll end up having a log of that probability. And so you're updating based on the gradient of the log of the probability in this case. All right. And you kind of have to go through the math to see why that log comes into the policy gradient theorem. Okay, so any questions? This is an algorithm. You could run it. It would probably work for reasonably, not super complex problems, but it would probably work for you for a lot of RL problems. Yeah. So that kind of takes us to where we were at the end of last lecture. So one problem with this is, we're using this G function. So let's just go back to the code. This G function to estimate, right? We're really using this as an estimate of the Q value of taking action A and state S. And it's kind of a myopic estimate in the sense that, or sort of a very simple estimate in the sense that it's only using that experience that we just got to estimate the Q function. And the estimate of the Q function ignores all previous experience, which probably has a lot of information about the Q function of action A and state S as well. And so what we'd like to do is somehow be able to leverage all of the experience to estimate Q as well. Notice here in this algorithm, we are using previous experience to estimate the value function. We have a neural network or a linear function here, and that's sort of always being updated and maintained, and that's our estimate for the baseline. Takes into account previous information, but G of T doesn't. So that's one thing maybe we could improve to make things better. And there's a fairly straightforward way to do that. We could use some sort of bootstrapping or temporal difference method for doing this. So this is what you'll hear in the literature about actor-critic methods. This is sort of what actor-critic methods are trying to do. And the actor-critic algorithms are really just versions of this generalized policy iteration that we've talked about before, where you're slowly updating the policy, and that's also being done in parallel with updating the value function. And so you're updating this value function, which depends on the policy, and updating the policy, which depends on the value function, and yet they miraculously converge in the generalized policy iteration framework. Well, actor-critic algorithms are doing the same thing. We're going to have an actor that is basically our policy, parameterized policy, and it's being used to select the actions, and it's going to be updated based on experience. And the critic is being used to evaluate the actor, right, to learn the how good is the actor in different states, and what is its Q function, perhaps. So there can be different types of critics. And the actor is then going to be updated based on the critic, and the critic is then going to be updated based on the updated actor. So you've got these things that are continually moving and trying to track each other, which can be problematic when you have function approximation going on, but often these things work out well, and it's sort of the best way to go about it. And you could take an approach where you're going to hold the policy fixed for a long period of time and update your critic and get a really good estimate of the value, and then update the policy based on that new critic and hold it fixed for a long time. People will do that sort of thing sometimes, but I think overall you find that updating these things more continually and it works out better. It's a better use of your resources. But there's really no theory that will suggest one way or the other. All right, so let's look at one version of a actor-critic algorithm, maybe one of the more straightforward but also pretty useful and effective methods. So remember, we've got our critic here, our actor here rather, which is the current policy. We're going to run an episode of it, and then we're going to, we also have our critic, which is going to be a value function estimate. And we can learn this using a TD temporal difference learning rule, right? That's something that we've already talked about before. And we could also, if we have this value function, we could just use it to estimate Q, right? And we've already seen one way to estimate the Q function is to say, well, what was the reward I just saw? And then what's the value of the next state, right? So what's the immediate reward plus what's the value at the next state I ended up at? And this is, if you remember back to temporal difference learning, when we were evaluating policies, this was sort of the target that you would give Q learning or just value function learning at the current state. So based on the current experience, what's my Q value estimate for the current state in action? You would use something like this. And we could also use that same V as our baseline. Right? So we'll estimate Q using V and the immediate R, and we'll use V to estimate the baseline. And then if we look at the advantage function, Q minus B, which our baseline is going to be the value function, we end up with this thing, right? And we've already seen this equation, right, in red. That's just the temporal difference error that we've already looked at previously. So this is our value function estimate of the for the current policy at the current state, S of t. And this is sort of the refined target estimate that we would like to have this estimate to be equal to, right? And so this target was the reward plus the value function at the next state. And that was the temporal difference. We saw that temporal difference learning is nothing more than using this to update the policy at every time, update the value function at every time step. All right. So let's look at that. So this is an actor-critic algorithm based on temporal differences. So very simple. We generate a trajectory each time through this loop, and then we go through all the time steps of the trajectory, and we're going to do one update to the critic and the actor for every time step. And so first we compute the temporal difference, right? And then we use that temporal difference for two purposes. The first, this is sort of what we already learned about in previous lectures. We use the temporal difference to update the value function estimate, right? And if you go back to your lecture slides, you'll see that when we talked about function approximation for policy evaluation, the temporal difference learning part was exactly this. And interestingly, we can, the temporal difference also, as we showed on the previous slide, was equal to, well, what we see in the policy gradient theorem, the Q function minus the baseline. So we can use the temporal difference for two purposes. That's what we get here. And we just basically do an update according to the policy gradient theorem. And that's all there is to it. So we compute one temporal difference and we use it to update both the policy and the value function. Just like previously, the only difference between this and our previous algorithm was we were using a different measure here to update the policy. So if we go back and look, what were we using in that algorithm? Instead of the temporal difference, we were using A, which was just a different way of estimating the baseline, the policy gradient. So Monte Carlo minus, here again we were doing the learned value function. And it just so happened here again that this was a valid way to update, to use for both of the updates. All right, so let's move on. So any questions about this? This is a pretty common structure to see, right? Very simple, right? There's nothing complicated about this. You can implement this pretty easily with standard deep learning libraries, right? So you would define your loss function for the value function to just be this, right? This would be your loss, and you would do a gradient update to minimize that. And you would define your loss function here to be in a similar way. So we've talked about that previously, and you would just update you would send that to the optimizer. So pretty easy to implement, and this is really the basis for a lot of policy gradient algorithms. And they're just adding different bells and whistles to these basic approaches. So we can look at, once you define this idea of actor-critic methods and you have the policy gradient theorem, you can define sort of an infinite space of different variants of these algorithms. So we know that this is the advantage function, and you could estimate the advantage function in different ways. And there's quite a bit of work out there that gives you different variants of ways of estimating the advantage function. Some of the more straightforward ways are you can use function approximation to estimate the Q function. We know how to do that. You could use function approximation to estimate the value function. So you could do one or both of those things. You can use Monte Carlo for one or both of those things. And if you do that, you get, this is just 4 different combinations of methods. So we saw if you just use a value function estimate, this is what you get. You get a one-step temporal difference actor-critic. You can also do an n-step bootstrap variant. And I'll show you this in a second when we talk about an algorithm called A3C. This sometimes works a little better, but we'll talk about that in a moment. But we did see this in previous lectures. You could do this. I don't know if I've ever seen anybody do this, but you could. And you could do this. This is a valid estimate as well that just uses the Q function. So this might not, I don't know if this second part makes sense to people, but this is just an estimate of the value function, right? We're saying we've got a probabilistic policy, and we're doing the expectation of the Q function over the probability of taking each action. And so this is an estimate of the value function. Countless variants, there's no rule about which of these might work best for you. People do lots of variants and add bells and whistles to these and give them names and try to show that they're better than somebody else's variant. Yeah, there's really no theory that tells you which of these is going to be best right now. So I wanted to show you at least one. I mean, we could have a whole course on, like I said, all of these variants and what things about the variants are most important. I want to get to some more material in this course, so I'm going to show you this one good baseline. I think it's not state of the art anymore, but what was state of the art yesterday is not state of the art today. These days. So things are changing fast, but this is a nice baseline algorithm. Lots of implementations out there. If there's time, I may talk about a couple of other algorithms later in the course, but this is the main one I want to show you right now. So this is called A3C for asynchronous advantage actor critic. Sometimes you'll see A2C when they remove the asynchronous part. So you'll just see advantage actor critic, and like based on what you've learned here today, you could guess what that would look like. But I actually want to talk about the asynchronous part because that was kind of interesting. So first, the A3C algorithm uses the n-step bootstrapping idea that we talked about previously. So the advantage function is going to of S of t and A of t is going to be estimated as follows. So normally we estimate the Q function by the immediate reward plus the value of the next state, right? The n-step bootstrap is you estimate the Q function based on the immediate reward for n steps. So you sum up the rewards for n steps, and then you add on the value function estimate for the n plus one state. Okay? So you're just using a little more of the real reward experience, and then you're capping it off with an estimate. And some value that Monte Carlo is the extreme where you use the entire trajectory's rewards and you don't have a value function estimate. TD learning, like basic TD learning, is when the other extreme where you just use the first reward. And it goes, sort of common sense that probably some value other than infinity and 1 is going to perform better in any particular application. So this n, for the n-step bootstrap estimate, this becomes sort of a hyperparameter of the algorithm that you can play with. And there's no theory about which value of this is going to be best. People have done lots of work of, there are ways of combining different values of n or all values of n. If you've ever heard about TD lambda learning, that's basically what they do. They'll do some sort of exponential averaging for different values of n. But more or less, it makes sense that some value of n that's not 1 or infinity will be better for some application. So just view this as a knob that you tune. Right, so this is the advantage, right? Our Q function estimate minus the value. Right, so that's clear. That can just, so A2C, without the asynchronous part, that's the algorithm. I showed you the previous page, right? The A2C is nothing more than this algorithm where we're estimating the advantage function using not just this, but the n-step reward. So it's a reasonably good way to go. But where they really got their mileage is with the asynchronous part, I think. We'll look at some results of synchronous versus asynchronous, and we'll see, well, the real value is the asynchronous part. So what they're going to do, so you can look at the details in this paper, and it's a reasonably good paper. I think they do a nice introduction to the various methods. They talk about different ways of making things asynchronous, And so it's a good paper to read, and you would all be able to read it if you've sort of followed the class. There's nothing deep in the paper. It's more of an engineering type paper. This is what the asynchronous part looks like, and you can imagine with your knowledge of Ray now that you would be able to implement this reasonably easily if you already had a version of, if you had everything else built, that you have to have. So there's going to be a global network. So think of this as the global parameter server for the network, right? And this is ultimately what we're optimizing. And at the end of the day, this is ultimately what we're going to return as, hey, this is our policy. So usually how this is done, and this is not anything set in stone, they'll often have the input fed to some sort of neural network which computes some features, and then that network has a policy coming off of it and a value function coming off of it. So it's predicting a value and the policy. This policy is often just, we'll see some examples. If there's a finite set of action, it's just you have a node for every action, and it's a softmax function over those values. So what's going to happen is we're going to have some number of workers, and each worker is going to have its own copy of an environment, right? So these workers are going to be completely independent of one another when they're doing this. And what the workers are going to do is they're going to just loop through the following. So first, the worker is going to copy the parameters, the current parameters from the global network, and they're going to do this all asynchronously. And then a worker is going to execute some number of trajectories in the environment and come up with gradient estimates, right? Using, we saw in the previous slide what that looks like. And then they're going to send the gradient estimates back to the server here, which will update the network and update the global network, and then the worker will get the new version and continue. So these workers are sort of asynchronously sending their gradient estimates to the global network and updating the parameters sort of all the time. And does that make anybody feel uncomfortable? Like what's something that might make you feel uncomfortable about this type of setup, compared to purely sequential? Or are you completely comfortable with it?
Mm-hmm. So it's like the first worker, say that the first worker first come back with the gradient aspect, mm-hmm. Come back. At the same time, all the other workers are still working on the previous one. Mm-hmm. So is that going to be a problem?
Yeah, so that definitely is something that can make you feel uncomfortable. Like that's the main thing. Is it going to be a problem? Well, it generally seems like it's better to do that. Now you could, how much delay there is, between updates. That's probably a big factor. If there was a lot of time and in between updating the network, maybe that could throw things off. But we'll see from the results that this doesn't seem to. It seems to be more of a win than a loss. So in other words, simulating the pure sequential gradient update doesn't seem as important as doing a lot more updates. Right? That's what people have found. But yeah, basically, worker N, workers 1 through 3 may have already sent their gradient updates, and worker N's gradient is based on the old network. It's sending its gradient update based on the old network. But we got to remember, all these gradients are highly stochastic approximations anyway. Right? Stochastic gradient descent is like any single gradient estimate is going to have some error, and this is just another little source of error. Maybe it's a big source of error sometimes. And so collectively, though, if they're pointing you in the right direction, it tends to work out better just to have more updates and more experience. Right? So, I mean, the other thing here that's kind of interesting is these are all exploring independently. So they can be in different parts of the space. In fact, the paper talks about, I forget what they experiment with, but you can have different exploration strategies for each of these networks if you want. They can be using different discount factors and different epsilons for the epsilon greedy exploration if you're doing that. Usually here they're just going to be executing a probabilistic policy, but that's one of the nice things too. This helps you explore the space much more rapidly than if you're doing things purely in sequence. Yes.
Yeah, I think if you can use different parameters like discount factors or like epsilons, but you should keep the network, the gradient somehow consistent because if you update your gradient on the current copy, but the global network is very different from the current copy of the network, it doesn't mean anything. So what good strategy may be to average all over the gradient and update and keep and make a copy of the global and simulate on different environments, so you get different gradients and average over the update.
Yeah. There's probably lots of and certainly averaging is something that people have looked at. So there are different strategies of trying to deal with this issue of outdated or stale, gradients. Uh, I think in general though, what I said is sort of my intuition. The stochastic gradient descent is sort of, these are noisy gradients anyway, right? We're just banking on the fact that if you do this enough, do enough updates with a lot of noisy gradients, it pushes you in the right direction. And so the fact that they're noisy gradients, it's a little bit outdated. Does it really matter? That's an empirical question. But there is a lot of there's a lot of work. I'm not an expert on it, on you know different ways of doing just pure stochastic gradient descent in a distributed way, and they're all trying to get at this issue somehow. And yeah, some things are empirical, but they also try to develop theory around this as well. Any other questions? Yes.
When doing a conjugate gradient update help
A conjugate gradient
instead of
update.
stochastic gradient?
I'm sure you could try to do that. Yeah, would it help? Yeah, it's hard to say. Sometimes not. That's most likely what you would find. But yeah, the stochastic gradients are just very fast and easy to compute. That's yeah. You often don't see people doing any fancy optimization things these days, surprisingly. Although there probably is room for even approximate second order methods, but people don't seem to be doing much of that. But there is work. You can find work on people using more complex schemes, and a lot of the work on optimizers is about trying to have more complex optimization methods. But certainly first order methods are the main thing that people are using. You generally don't want to be computing Hessians or anything like that. Yeah. Any other questions? All right. So this is, as I said, you would be able to implement this pretty easily with Ray. Right? This you would define. I mean, there's variations on how you would do it. You'd have to play around with what's going to be best. But if these environments are non-trivial in terms of how long it takes to execute experiences, it's going to be worthwhile to move these parameters over and execute experiences independently. If the environments are like so fast that the overhead of moving the data around isn't worth it, then yeah, you'll have your trade-offs. But yeah, you would define some actor as a server, and then you could create actors for workers, or you could just you could use the approach that we saw worked well for the value iteration experiment is from the main program. So let's see here. So this is from their paper. So I'm just showing you some results from this paper. I don't know what you'd see these days if you were plotting the state of the art, but they would go up a little faster maybe. But this is showing you a bunch of algorithms. So DQN, this is non-distributed DQN. One-step Q-learning, one-step SARSA, and so this is n-step Q-learning, and then this is the asynchronous version. Okay, and the asynchronous version is being trained with 16 CPU cores. There's no GPU, and the DQN is trained with one GPU. Now, these are Atari games, so you're dealing with images as input, so GPU could have a little bit of an advantage there. But we see that A3C, this is wall clock time, right? It uses wall clock time, a lot less wall clock time to get a certain level of performance. And of course, the actual time, it's using 16 CPUs, so you might have to multiply that wall clock time by 16 to get actual CPU time. But often what we care about is wall clock time if you already have these resources. So you see, there's a pretty big increase in performance. It's pretty impressive. And this was really one of the first. I mean, there had been some people dabbling in this, but this is one of the first real demonstrations of asynchronous training really showing a big value. And now there's more work that does that. So you see that for these other games as well. But we're still talking. To train a Pong policy at that time, it was still 4 hours of training.
I'm just curious if there's a well-known explanation as to. I noticed that for Pong, they tend to be pretty close to one another versus Cubert in particular. It seems to have a much better learning rate than any of the others, or even compared to Breakout.
Yeah. I mean, it's hard to say. I mean, Pong is probably the easiest of these games, so it requires the least amount of experience. So that's maybe one explanation there. Just Cubert's a harder problem, so it requires more and more experience to get off the ground. Like often with these types of problems, there's sort of a experience threshold that you have to get, right, so that you start getting some traction. And once you get, in Pong, once you start getting enough experience so that you learn that hitting the ball is a good thing, then you start getting traction, because then you can start thinking about, well, what's the best way to hit the ball? And the same thing with Breakout. And it's sort of how much experience do you need to get to that point? That's one way of thinking about this. And so maybe that point was reached right about here for them, and that point was reached about here for A3C at least, where you get that accelerated improvement. But there's really no theory about this. Any other questions? All right. So another way that you can sort of slice up the data, another experiment they have in the paper, and then they show experiments for a lot more than just these 3 domains. I think they have numbers for 50 plus Atari games, and they also have results for some of the continuous control domains with the Mojoko simulator. So this is showing what happens when you use different numbers of threads. So 1 thread to 16 threads. So that would equate. I don't know if that equates to the number of workers. Number of threads is -1 is the number of workers. That's what I'm guessing. I don't know, but roughly number of workers, 1 worker per thread. And you can see there's the number of threads is critical. right? And if you only use one thread, this is something I didn't realize until I went back and looked. Like I was always curious because DQN seems like a very easy to it seems very easy to make DQN asynchronous, right? You're gonna go collect some experience, very similar to this. Do a mini batch or two and send the gradient back to a server. And I was always curious. Well, is A3C really better than DQN fundamentally, or is it really just the asynchronous aspect? And this curve lets you kind of see that. So if you have A3C and you look at the performance, after, this is close to 15 hours with one thread, not doing terribly well, right? Then you go to DQN with one thread. Now DQN is using a GPU here as opposed to a CPU, so you got to account for that. But we see that it's doing quite a bit better after that amount of training time. So A3C being fundamentally better than DQN, it seems from these results it's really due to the asynchronous part. And so, I haven't seen a paper. I haven't actually looked too hard that evaluates a lot of different algorithms with asynchronous variants tested. So that would actually be interesting to look at. And you're going to get to do an asynchronous DQN. We're probably not going to be able to do Pong. That's my guess, because our initial test, it's just, unless you want to be trying to run on DevCloud for multiple hours, which probably is not going to be very robust for you. We're going to pick some simpler problems, but it will still be interesting. So my original goal of having you train on Atari, probably not going to get there. We'll see. We'll see what Zheng Xian comes up with. Is that what you're guessing?
Yeah, actually, I'm thinking trying to try some simple game like couple or blender to let you train on it.
Yeah.
But I think the pond is possible to do that because I'm changing something, but there is no result to talk about now. So
Yeah. So we haven't tried the asynchronous version yet. This is why we're a little bit of delay for the assignment. The synchronous version, you're down to like 10 hours or something, or 20 hours, or
actually, I'm changing something. Maybe I can change it within 5 hours.
yeah.
So
But still, that's kind of progress. But you don't want to have to train for 5 hours. I don't think.
Yeah, but there is one thing: is the work time of the dev cloud is 6 hours. So
Yeah.
yeah,
So
it's really short.
that'll be an issue. So we'll see. When we add the asynchronous part, who knows what will happen. So it's an interesting algorithm, but yeah, it seems like the single core version isn't really that great, which was an interesting insight to have. Yeah, so concurrency is critical, and this is just another table. So this was, again, some of the state of the art at the time, just showing you sort of the different numbers of training periods. So yeah, we don't have to go through this in detail. You can look at that on your own. We'll look at the paper. So the trick there was adding some asynchronous aspects to the algorithm. There's one more trick that's pretty common. Maybe it's becoming almost universal for policy gradient methods. And we'll just call it trust regions, but there are various ways of implementing this sort of thing. But the key idea, I'll just talk about it. I have a lot of words there. Is in policy gradient methods, you're going to adjust the policy in some direction, right, according to this type of update. And the learning rate sort of says how much you're going to adjust. Now, if you adjust it too much, you change the policy so much that it's nothing like the policy that you estimated the gradient from. And you could be in a completely different part of the space, and it's the estimate of the performance gain, right? So the gradient is really just a gradient around the point you're at, right? It's saying if you make a small change around the point you're at, you're going to improve. But it's really hard to figure out how far you should move. And if you move too far, you can completely change your policy. And what will happen, I see this all the time. You'll have a robot that might have been trying to walk a little bit, then you update the policy, and now it's just falling on its face every time. And now you've got these policy parameters where it's just falling on its face every time, and you can't recover from that. Like there's no number of gradient updates that will make it not fall on its face because it's such a bad policy, gradients are not good enough to get you out of that. And so what people will do is they'll essentially try to somehow limit how far you move the policy away from the current policy, with the idea that the gradient estimate is going to be reasonable around the policy that we're currently at, and so they'll limit it. And there's several ways of limiting that. The complicated way is, it's a nice paper called Trust Region Policy Optimization. They have a very complicated way of limiting this that involves optimization algorithms in the inner loop. We've implemented that. We've got implementations of it, but it's a very hard thing to implement correctly because it has all of these inner loop optimizations. The simple way is a new algorithm, well, relatively new, called PPO, Proximial Policy Optimization. They effectively just put a limit on, how much you can move it. That's effectively what they do. I'll put a pointer to that here, and that's much easier to implement, and seems to work about as well as Trust Region Policy Optimization. So that's often how things are limited here. So if you're interested in that, that's just another very common trick, very important, because if you do an update that just crashes your system, you've got a policy that you can't recover from at that point. And so limiting the updates is pretty critical. So I guess we'll stop there. Next time I'll just show you a couple of ways of representing policies. We'll show a few examples, and then we'll be done with policy gradient.